Have you ever just stopped and wondered, how does a digital idea, just a bunch of pixels on your computer screen, turn into a real, solid object you can actually hold in your hand? It feels like it should be magic, right? But it's not. It's the reality of modern engineering. And today, we're going to pull back the curtain on that incredible journey, from pixels to precision parts.
Just take a look at this. I mean, wow. The smooth curves, those perfectly placed holes, it's an absolute masterpiece of precision. But here's the crazy part. A little while ago, this thing, it didn't even exist. It was nothing but data, just a digital blueprint floating around in a computer. And that incredible process, the one that turns pure data into physical reality, that's exactly what we're diving into today.
So how do we bridge that gap, between the virtual world and the physical one? What are the key technologies that make this whole transformation even possible? Well, that's the big question we're here to answer. So let's break it all down.
This whole idea of telling a machine what to do, it's actually not new at all. It goes way back, all the way to the 19th century, with things like programmable looms and even player pianos. But the modern era, that really kicked off in the 1940s with something called numerical control. It was this revolutionary idea of using punch tape to guide every single move a machine made. Then, in 1952, there was a huge breakthrough at MIT that proved the whole concept could work, and that right there set the stage for the amazing automated systems we use today.
All right, so every single physical part has to start its life somewhere, right? And today, that somewhere is a digital blueprint, which means we always begin with the first absolutely crucial step, computer-aided design, or as you probably know it, CAD.
So what is CAD exactly? Well, you can think of it as the ultimate digital sandbox for engineers and designers. It's this super powerful software that lets them build incredibly detailed 2D or 3D models of, well, pretty much anything. The key thing to remember is, before a single piece of metal is ever touched, the entire object is built and perfected virtually, piece by digital piece.
Yeah, another great way to think about it is like this. CAD is the ultimate digital drawing board. It's the place where a fuzzy, abstract idea gets sculpted into something real. It's where it gets its precise dimensions and gets defined down to the tiniest, most microscopic detail. Seriously, everything the final part is going to be, that's all decided right here in this virtual space.
Okay, so now we've got this perfect digital blueprint. Awesome. But let's be real, at this point, it's still just a fancy picture on a screen. The big question is, how do we translate that beautiful design into a set of instructions a machine can actually understand and follow? Well, that brings us to the next player in this game, the strategist, computer-aided manufacturing, or CAM.
If CAD is the what, the final design, then CAM is the how. It's the absolutely essential bridge that connects the design to the actual production. This software is smart. It takes that CAD model, analyzes it, and then generates a super detailed step-by-step plan for manufacturing. It figures out the exact paths the cutting tools should take and all the instructions the machine will need to follow to carve the part out of a block of raw material. So let's just nail this down so it's crystal clear. CAD is the designer. It's all about creating the model. CAM, on the other hand, is the strategist. Its job is to figure out how to actually make that model. You could say CAD defines the shape, the geometry, while CAM defines the action, the motion. In modern manufacturing, you absolutely need both. One just can't do its job without the other.
So this brings us to the core workflow. And honestly, it's a pretty simple three-step process when you boil it down. Step 1, you create the design using CAD software. Step 2, you generate the manufacturing plan, the toolpaths and the machine code using CAM software. And finally, step 3, you send that plan over to the CNC machine to actually make the part. It's that simple. Design, plan, execute. That's the mantra.
And this flowchart really lays it all out perfectly. You see, it all starts with a need, a demand for something. That demand sparks the design, which is created in CAD. From there, that digital design flows right into the manufacturing phase, which is all planned out by CAM. It's this beautiful, seamless, integrated system that takes an idea from just a thought all the way to a finished product you can hold.
Okay, so we keep saying that CAM creates instructions, but what does that actually mean? What do those instructions look like? Well, they're written in what's basically a universal language, one that pretty much every CNC machine on the planet can understand. And that language is called G-code.
G-code is, at its heart, the fundamental programming language for all CNC machines. The best way to think of it is like a script made up of super simple text commands. And its universality, that's the magic key. It means you can design a part in Texas and have it made on a machine in Germany. No translation needed.
Every single line of G-code tells the machine's motors exactly where to move, how fast to go, and the precise path it needs to follow. Now, I know a line of G-code like this can look kind of intimidating, like something out of the Matrix, but I promise it's really not. This line right here, it's just a simple command. G01 just means move in a straight line. The X, Y, and Z values, those are just the coordinates, the destination. And F sets the feed rate, that's the speed. So all this line is saying is, hey machine, move in a straight line to this exact spot at this specific speed. That's it. A whole manufacturing program is just thousands of these simple little lines, one after the other.
Okay, let's recap. We've got the blueprint from CAD, we've got the master strategy from CAM, and we have the language G-code to communicate that strategy. It's finally time to bring it all together for the main event, the execution. This is where the real star of the show, the CNC machine itself, takes center stage.
When you get right down to it, a CNC machine like this mill is a brilliantly simple concept. All it's doing is moving a spinning cutting tool with insane precision along 3 axes, X, Y, and Z. And as that tool moves, it removes material from a block that's held perfectly still. We call that the workpiece. It's literally carving the final design out of a solid piece of raw stock. And here you can see that concept in action. On the left, you've got the clean, neat schematic, and on the right, you've got the messy, loud, dynamic reality of metal chips flying everywhere. But it's this very simple principle, a precisely controlled cutting tool that lets us create unbelievably complex shapes with pinpoint accuracy over and over and over again.
But hang on, there's a super critical detail we can't ignore. For the machine to be accurate down to thousandths of an inch, that's thinner than a human hair, the workpiece cannot move. Not even a tiny bit. It has to fight against the immense forces of that cutting tool. And the whole science and art of holding that part perfectly still, that's called workholding. And, as you can imagine, there are a ton of different ways to do it, all depending on the part shape and what it's made of. You know, machinists might use a simple vise, or they might build totally custom fixtures for really complex parts. They might use a system of clamps, or even, get this, vacuum tables that literally use suction to hold down thin, delicate materials. Whatever the method, good workholding is absolutely essential for good results. No way around it.
So, we've followed the entire journey now, from the initial design to the plan, all the way to the final execution. But let's step back for a second. Why is this whole integrated system so revolutionary? Why does this seamless connection between CAD, CAM, and CNC matter so much in the world of modern manufacturing?
Well, the power of this automation is just staggering. All of a sudden, cutting a complex, swooping curve is just as easy for the machine as cutting a perfectly straight line. That alone just blows the doors off of design freedom. Your quality and consistency, they skyrocket because the machine does the job perfectly every single time, practically eliminating human error. And all of this gives manufacturers a level of flexibility and productivity that they could have only dreamed of just a few decades ago. What it all boils down to is this. The integration of CAD and CAM completely obliterates the gap that used to exist between the design office and the factory floor. It's like building a superhighway directly from the mind of the designer straight to the physical movements of the machine.
And that brings us to really the single most important takeaway of this whole thing, the digital thread. That's the big concept here. It's this idea of an unbroken, seamless connection that runs all the way from that initial 3D model to the finished physical part in your hand. This digital thread, it's the core innovation that has completely revolutionized how we make just about everything in the 21st century.
This whole process means we can now manufacture parts with a level of complexity and precision that was, not that long ago, pure science fiction. And that leaves us with one really fascinating question to chew on. Now that our ability to create physical objects is limited only by our own imagination, what on earth are we going to imagine next?